Okay, guys, we're going to bring our attention to humoral immunity today. We know now that humoral immunity is part of the adaptive side of the body defenses. We know that there is going to be some antigen involved, and in this case, because it's a body fluid with antibodies, there are going to be some antibodies produced. All right, so we're going to focus on these fluids that circulate throughout the body, like blood and the lymph, and contain these antibodies. They're certainly not the only fluids that contain antibodies, but they're circulating in this fashion. And it so happens that cells are responsible for producing these antibodies. They're a protein after all, and they are coded for on DNA inside the cells, right? So when we talk about cellular immunity, I don't want you to confuse B cells for cellular immunity. B cells are going to be attached to the humoral side. Even though they are a cell, they are all about antibodies. All right, so when we think humoral, we think adaptive, we think antibodies, and we think B cells that produce those antibodies. Now, an activated B cell that produces antibodies and secretes them after they're exposed to a certain antigen are called plasma cells. And we're going to talk more about that here in a second. Right? We call them B cells because they are actually going to be trained within the bone marrow. So the B is for bone marrow. And this is one aspect about B cells and eventually T cells that makes them a little more sophisticated. They are trained in a way. They become immunocompetent, we would say. Makes sense, right? They are competent to be part of our immune system because they are trained in a way so that they can tell the difference between self and non-self proteins, all right? So they are immunocompetent. I always think of these B cells not as a security guard or just a phagocyte, right? I think of them more like they went to college, right? They went and they learned the specific differences between what is self and anything that's not like that would be non-self and foreign, something we might need to do something about. So here we have an image showing 3 different B cells, right? 3 different B cells. And let's say we have these B cells and they're sitting in our system right now, and you're exposed to a certain foreign antigen. And the foreign antigen is here, these little red dots. What specifically is it? I don't know, make something up, right? Could be a toxin from a bacterium, could be a protein off of a virus, but it's not self, right? Now, when I go over this, usually in A&P, I'm going to do it again here. I usually use screwdrivers, all right? So I think of the proteins that are on these B cells, which are antibodies, okay? So think of this as an antibody, right? This screwdriver, and it's sitting on the surface of the cell, right? That antibody is going to have a certain shape to the end of it, okay? So if I think of the screwdriver like an antibody, I see a Phillips head end here that would fit a Phillips screw, okay? I see a flat end here on this screwdriver, okay? I see a hexagonal structure here for like a nut or something, right? So these are sitting on the surfaces of these cells, and each cell will typically have one shape to their antibodies, all right? Now, if that particular antibody fits an antigen, like I've got a screw here, which is a Phillips head. I know you probably can't see it, but it's a Phillips head end on the head here. And this is a good example of an antigen with lots of shapes, right? Lots of epitopes. I see it. There's a point on one end. There's kind of these ridges here on the edge of the screw, right? There's the head part, and then there's that dimple on the inside of the head, which is where the screwdriver fits, right? So if I am testing this screw on all of these different antibodies, like this head, this flathead is not going to fit this screw very well, okay? Not very useful screwdriver. This hex end, not going to fit very well. But this Phillips head is perfect. This Phillips end is going to fit that perfectly, right? So that epitope on the antigen fits this end of the antibody perfectly. This is the screwdriver we want to keep around, right? So this Phillips head fitting here, right, is our second B cell. That B cell is the one we want to clone, okay? So that's exactly what's going to happen. That B cell is going to be cloned. It's selected for the fact that it attaches to the right part of an antigen, one that is foreign. And these guys are going to pass ultimately. These cells are going to pass away. They're going to die. They have a certain lifespan. And this B cell is going to be kept around. Ultimately, some of these B cells that divide off, daughter cells of the original, are going to look just like the original. But some of them are going to be plasma cells. They're going to be cells that are capable of secreting their antibodies. Okay? So imagine, okay, this stuck to me. I'm one of the B cells that's going to be activated and cloned, right? And then progeny from this B cell would then secrete maybe more slightly different antibodies because they're secreted, okay? But they still have that Phillips end, right? They're still going to fit that particular head of the screw, okay? So our primary response is going to be what we just went through, okay? There's going to be a contact, a selection of a B cell during the first exposure, and it's going to take time. It's going to take a bunch of days, right? Maybe a week for this to happen. So it's slow. But once these antibodies are there, they're going to help with our immunity. They're going to be like the soldiers of the immune system, okay? Now, after all this initial infection is over, we're going to have memory B cells that stick around. These memory B cells will be in higher abundance, but they all have that Phillips head end, and these are our memory. This is the building part, right, where we build this memory. Now when we get exposed to this particular toxin or bacterium with this antigen again, we are going to have a very quick secondary response. It's going to be faster due to the fact that there's memory, and much more robust. Many more antibodies are going to be produced and secreted to help us. And we may not even feel the effects of this second exposure because it's so fast and it really disposes of the pathogen quickly. Okay? So here we just see some differences between a B cell. So here's a typical B cell over here on the left. But then here we have our plasma cells. These plasma cells have rough ER. They're rough because of ribosomes, you may recall. And so all of these little ribosomes here on the ER are protein factories, proteins being antibodies, right? These are going to be secreting those antibodies for our benefit. Now, some of these antibodies are IgMs. We have classes for each of these. But when we take a concentration from the bloodstream of the different antibodies, we call it a titer, okay? So a serum antibody titer could be a measure of IgMs or some other class. Typically, we're looking at IgG levels, but it all depends on what it is we're trying to find out. IgMs are usually going to be produced in higher concentrations early, and then later on, we'll find that IgGs are going to be more abundant. Okay? And you'll notice the big difference between a primary response and a secondary response. Secondary response has a much higher abundance of IgGs being produced because there are memory cells involved. You might recall they talked about IgMs and IgGs in that COVID-19 project, okay, where they're looking at IgMs and IgGs in response to the coronavirus. And this is one serological test, right, because they're taking serum for seeing if someone's been exposed or not. Now, how it is that we acquire antibodies really makes a difference, and it really matters, okay? The best scenario would be for me to have for my immune system to have memory cells. Because if my immune system has memory cells, then I can knock out that particular pathogen or antigen any time I get exposed in the future. If I don't have memory cells, then I can't make those antibodies, right? The fact is that I need to be exposed to something in order to have those memory cells. So what I really want is an active immunity. Whether that immune system is activated through exposure because I got sick, an actual infection, right? Like you catch a common cold, for example. And the hope is you fight that cold off, right? And as a result, you're stronger for it. You've built an immunity, okay? Now, where some viruses and bacteria are extra nasty, right? So they can get the best of your immune system, and the body systems have trouble fighting it off. And that's what we're worried about, definitely with coronavirus, right? Because depending on your level of your immune system and pre-existing conditions, you may not be able to fight it off, right? 80% of individuals are able to fight it off, and they're better off for it. They're going to have an immunity to that virus, at least for some period of time. So with that particular scenario, I'm going to have memory. I'm going to put a big letter M here, and that's the great thing about activating, is you're going to have a memory. Now there's another way that I could get exposed, and that would be if I am vaccinated against something, okay? So if you give me boosters or a vaccination, you're actually exposing me to the antigens that are associated with a nasty pathogen. You're either kind of grinding up the pathogen and just injecting the proteins, or there are attenuated forms of these pathogens, live but weakened forms of these pathogens, all right? Whether they be viral or bacterial, all right? And what they do is they also expose the body, right? You're going to have your selection of B cells and memory ultimately. So again, another big M here. Great thing about vaccinations, right, is it exposes you, and now we have the ability to produce those antibodies. Now, the difference between the two, if we had to put a name to it, would be one is naturally going to happen, right? People get colds, people get sick. The other is artificial, and we don't see other animals doing these things, right? Like it usually involves a syringe or something, right? So artificial is kind of this vaccination idea, okay? All right, what about passive? So for passive, the word implies that I don't really do anything. I'm passive, right? I don't do anything to get my antibodies, to make my antibodies. I don't activate my immune system so that I can have these antibodies. So a great example here would be antibodies from the mother, whether it be through the mother's milk, okay, or through the placenta, perhaps. Antibodies might be passed. Now this will give protection to a child, right? But that child doesn't have memory. They have to do that once they're born. They have to get exposed to things and build that kind of immunity. It's not going to be everlasting, right? The fact that the mother passes certain antibodies through the placenta. Now that's a natural way for things to occur, but there are also artificial ways we can introduce these antibodies. If you know someone who's been exposed to something and you know they're making antibodies, you could isolate those antibodies from that person, purify all that, right, into one kind of injection that you would introduce into another person. I'm not sure if they'd inject it or introduce it in some other way, but they would have some way of actually putting that into the bloodstream of an infected person that is incapable of producing their own antibodies. Maybe their immune system is not doing that very well for them. And so that kind of injection of some kind of antibody would be a passive but artificial way of introducing these antibodies. All right? And this, I believe, is one thing they're looking at when it comes to treating possibly people who are failing to survive coronavirus infections, is by, could we come up with some kind of an antitoxin in a way, right? An anti-coronavirus injection with antibodies. All right, so what exactly do these antibodies look like? First of all, they are absolutely a protein, and I will oftentimes use these terms interchangeably, antibody and immunoglobulin. Okay, they're one and the same. And there are actually several proteins that come together to make antibodies. Two important aspects about an antibody I want you to know will be what a variable region is versus what the constant region is. Okay, so variable region is going to be on the ends of the Y-shaped structure here. These are variable regions. These are the regions that attach to the specific shape on the antigen. Okay? Versus the rest of that antibody, which is going to be the constant region. Okay? So, something that people sometimes mess up, so I just want to pause and say this. The variable region of an antibody, right? A variable region is part of the antibody, would bind to the epitope on an antigen. Right? Epitopes are the mini shapes on antigens, and these variable portions are going to bind to them. So in my little scenario here, right, this is the antibody, this would be the variable portion. And then this would be the epitope where that variable portion attaches to the antigen, okay, when it comes to this little kind of analogy here I have. So what do these antibodies actually do for us? They're the soldiers of the immune system. They're far more abundant than the phagocytes are. They have to be doing something to protect me. One of the things antibodies do is they neutralize antigens. These antibodies will cover antigens to the point where they will actually cover up the active site of antigens. So let's say, for example, I'll just draw a little example here. If we have an antigen which is actually an enzyme. Let's say we have an enzyme from Staphylococcus aureus, and this enzyme eats up our collagen. So when we get a staph infection under the skin or something, then these enzymes help that bacterium to grind up the collagen and eat it. Okay? Bacteria do that. If we have antibodies, we'll go to yellow here. If we have antibodies and those antibodies have a shape to their variable portion, so let's have that be a variable portion of the antibody, right? Kind of an arrow shape here with a triangle shape. And this particular antibody now is sticking in the active site of that collagen enzyme, then that will neutralize the activity of that. It's not going to be good for the bacterium because they're trying to eat here, right? So this would be one activity the antibodies help us with. They're going to block up bacterial enzymes and things like that. Agglutination. If I take 10 people in the classroom, of course, usually I have you guys in front of me, right? But if I take 5 people that you find anywhere out in the public, right? Find 5 people in the grocery store and you just put a big rope around them, they're not going to go about their day the same way. Well, in the case of agglutination, remember these antibodies have 2 sticky ends, at least 2 variable portions. So if I stick a variable portion to one antigen surface antigen on a bacterium over here and one surface antigen on a bacterium over here, they're going to be bound together. Now, if they have flagella, they want to do their own thing, right? But if with agglutination, you clump the cells up, you see. Okay, so that's going to really interfere with bacterial infection. Precipitation. Many antibodies will cause the various antigens produced by bacteria to precipitate and become a solid. All right. A common example might be a toxin. Toxins do their thing as a dissolved substance. Toxins cause us a lot of problems sometimes. They're the main problem sometimes with bacterial infections. And for example, diphtheria makes toxins in the back of the throat and causes lots of redness and inflammation there in the back of the throat. So what do some of these antibodies do? They stick to those toxins, and suddenly the toxins are a solid form, they precipitate, and they don't do what they typically do when they're dissolved. Finally, through the action of antibodies, there is an interaction between phagocytes and anything that an antibody is attached to. Phagocytes have the special ability of recognizing the constant end of antibodies. So when an antibody is attached to a bacterium, the other end is free for phagocytes to grab onto and engulf that particular foreign entity. Okay, so there are a lot of mechanisms by which antibodies work. Finally, there are also a lot of different types of antibodies, a lot of classes of antibodies. We've talked about IgGs. These have, like a Y, they have two sticky ends, okay? Two variable portions. They're most abundant in the plasma of the blood. And these are the ones that we often measure by taking a serum and an antibody titer from the blood, okay? We're measuring primary and secondary responses. These are circulating, and they're going to attack bacteria, viruses, toxins if they get in the blood. And these are the little guys that can actually go across the placenta. So these are the ones that are helping the fetus out, and even after birth, these antibodies are going to help to an extent with immunity. IgDs look very similar, but these are the actual antibodies that are attached to the cells. Okay, so in an original B cell, this attached antibody with the variable portions sticking out, these would be IgDs. Okay, so an IgD is stuck to a B cell. It's the original receptor for an antigen. Versus IgGs, which are circulating in the humors, right? Here, circulating in the plasma in this case. We have IgEs, also look very similar, but these are more abundant in the skin, GI tract, so that's the digestive tract, and the respiratory system. Okay, they're very active in those regions, and unfortunately, they are the culprit when it comes to a lot of our allergies. They're often abundant for people that really suffer from allergies. And if you think about it, that kind of makes perfect sense, because some of our more problematic allergies are skin related, right? People get rashes and things like that. GI, food allergies, and respiratory, right? People have horrible respiratory allergies, pollen and mold spores in the air, other chemicals that can really cause people to go into some problematic respiratory issues. We have IgAs. Check out those, right? They've got 1, 2, 3, 4 variable ends. They must be real good at attaching to 4 different antigens, okay? And those are found in secretions. So these would be like mucus, saliva, sweat, milk. There's some that aren't listed here. Tears, vaginal secretions, even semen will have IgAs, okay? And generally, these particular antibodies will bind up antigens on the surface of bacteria that oftentimes the bacteria will use to attach to you. Okay, so this prevents the antigen attachment and bacterial attachment oftentimes, or viral attachment. Finally, we have IgMs. Think M and think more. Okay, we have more antibodies, more variable portions to this antibody, I should say. Okay, so it's more variable portions. We have a pentamer. We have 5 times 2 variable ends. This guy is really good at agglutinating. Remember, agglutination is when you clump up cells. Well, if you had a cell with an antigen for each of those variable portions, you could actually clump up 10 bacteria. They're not going to go about their day the same way, right? Because they're all going to be kind of tied together by this particular kind of antibody. All right, that was a little longer one, but humoral immunity is really important. We need to understand antibodies. They're a big part of testing, like you may have found in our COVID-19 project. Let's leave it at that, and we're going to jump into the cellular side next. Okay?